All right, these are your video notes for 4.5. The topic today will be inverses, but before we get into that, we're going to do a little bit of recap review, and actually I think I would call this an extension of working with exponents. And so to be able to do these kinds of problems, what we're looking at here, we're going to have to figure out how we can somehow manipulate one side of the equation to give us what's called a like base. Because if you check out your exponents, or where your variable sits, I should say, your variable sits up in the exponent. And to be able to pull this off and solve for x, we're going to have to do some kind of manipulation here. In order to be able to manipulate the red numbers, here's what you're going to have to be thinking about is, how can I relate it to the other side? In other words, this base. So this is a base 9, a base 2, a base 4. How can I relate 81 to 9, 8 to 2, and 1/16 to 4? And to do that, we have to change 81 to a power of 9. Now, if I ask you guys 9 to what power is 81, that's a question everybody should be able to answer, because 9 squared is 81, and we all know that fact. This exponent 2 on the outside, just coming with for a second. Now I'm going to apply a rule of exponents that we all should know, which is a power raised to a power is multiplication. So 2 times 2, I'm going to have 9 to the 4th. And then when you get to this point, especially on this one, because this is a lone x, it's as simple as, what does that x have to be equal to the other side? Well, it's got to be 4, right? When we get over here and the exponents have a little bit more going on, we'll do a little bit of algebra to kind of make sure we're clear on that, but same approach. So as I look at the base 8, what I want to do then again is say, all right, I got 2 on this side. 2 to what power is 8? Again, one you guys should probably know. You should really know your powers of bigger than just squares, I should say. So not just squaring something, but can you cube it? Can you raise it to the 4th, to the 5th, and so on? And so I'm thinking 2 to the 3rd is 8. Again, that x is just traveling with. So 2 to the 3rd being 8, I'm going to use the rule of a power to a power and multiply those two together. So 3 times x is 3x. And then here, you could try to reason it out, I suppose, with the 5x minus 2 and 3x, but the easiest way to do it, if you want to be 100% sure, is just create a little mini equation out of your exponents and say, let me set them equal and solve. Because at this point, with the base being the same, you can do that. A little bit of basic algebra here, and I got it. So I subtracted 3x, I added 2 to the other side, divided by 2, and there you go. Here with the fraction, we're going to have to focus in on the denominator, because 16 is what we're going to relate to our 4. So I'm going to start out with that, and what power of 4 is 16, so that'd be 4 squared. The fact that it's in the bottom of fraction, we can deal with that, and remember another rule of exponents says if we have a 1 over, and we want to get rid of it, we can get rid of that fraction by basically making the exponent negative, or move it up or down in the fraction. So that's what we're going to do. We're going to take that 4 squared, and we're going to move it up, get rid of the 1 over, and now we've got 4 to the negative 2, which is equal to 1 over 4 squared. Power to power, multiply those two exponents together, set up my mini equation with my exponents, a little bit of basic algebra, and I got it. So it's a good way to get you thinking, how do I solve for a variable that's an exponent, and how do I manipulate the base, at least on one side, to make that possible. Okay, let's get into inverses and see what's going on with our inverse topics today. So the idea today is definitely all about building meaning that we're going to just build up the ideas, get you guys used to what inverses are about, and then we can always go further with that when we go through the chapter. Basically, the fundamental idea of looking at a function and its inverse revolves around one topic, or I should say one idea, and that idea will be woven in through everything we do, and that is the exchange of x and y. So that is really the goal here as we go through the rest of the notes, is thinking about how that is a theme throughout every single thing that involves inverse. And as we do that, we'll hit all these different bullet points here. The first thing to do is discuss what inverse relationship means. And inverse means opposite. And so I kind of got basically a word model here for you guys to think about. As A increases, B decreases. That would be an inverse relationship. If it was direct, then it would be increase, increase, for example, or decrease, decrease. So it's an opposite effect. And think of, there's lots of examples of things that have inverse relationships in your life, and this might be true especially in our distance learning environment, but as your stress increases, your performance might decrease. So as things get more stressful, sometimes you have a hard time performing. That's definitely can be true in lots of instances in life. So that's a basic word model, and just kind of looking at something you can think about that might be true in your life, or maybe not, hopefully, right? But as we go to coordinates, that's a simple idea of switching x and y. So the main idea, and this again, we're going to come back to this over and over and over again throughout the notes today, is the main idea when we talk about inverses is the switch of x and y. So if I say A is my original and B is its inverse, then you notice how I've switched the coordinates, and graphically, there's my A and my B. If that's my C coordinate, I say what's its inverse coordinate? Its inverse coordinate again be the switch of x and y, so that you see the switch going on. And then the generic way of talking about it is if I give you a coordinate x comma y, what would its inverse coordinate be? You would switch them. The idea, there's one more thing also to think about too, is the fundamental relationship that exists between all inverses, right? Which is definitely switching x and y somehow. So if we take that idea of coordinate switch and now we look at some graphs, what we're going to do here is try to, again, get that relationship going of the switch of x and y. That is a theme throughout, for sure. And here's the original function. Now we're looking at a parent function that we should know from past chapters, right? So we're looking at our quadratic, our parabola. The idea would be to take a look at the coordinates that I have plotted in the original, and then we're going to try to decide which one is its inverse, which will be really easy to do. All we'll have to do is go do the coordinate switch and we got it. So the first thing I would do is I would list out those coordinates. So here's a list of coordinates plotted on the parent function, or f of x equals x squared. Now as I start to search through the other graphs, what I want to do is one at a time go down through my coordinates and switch them. The 0, 0 coordinate, you'll notice, is not actually that helpful because 0, 0 is in all of them, and switching 0, 0 doesn't really help me understand which one of these is its inverse. But as we start to switch more and more of them, you'll see it develop pretty quickly. So 1, 1 switched is still 1, 1, so you might feel like that doesn't help, but actually look at where it shows up and not on the others. And now you'll start to see the switching going on, so we'll do 2, 4 is 4, 2. Negative 1, 1 is now 1, negative 1, and then our negative 2, 4 is 4, negative 2. So this C graph is clearly our inverse function. And it's as simple, and if you're even asked to draw an inverse, like I give you that original graph and I say draw its inverse, it's be as easy as what I did right there. Just take the coordinates from the original, flip the x, y values, replot, you just drew the inverse. Also, we're going to just do a little flashback to transformations from last chapter, so kind of remind you guys of some of those ideas. The question here is the A and the B graphs, how are they related to the original by transformation? And if you look at the original compared to A, and the original compared to B, these are clearly reflections. So this is a reflection over the x-axis. This is a reflection over the y-axis. And so, we just make a quick note, like a reminder what type of reflection we have and what's going on for transformation. So reflection over the x being the A graph and reflection over the y being the B graph. I also wrote below besides just stating the type, how you would write it. And remember, negative out in front, or make the function negative, reflects over the x-axis. Make your x value negative, reflect over the y-axis. So a little flashback to chapter 3. Okay, let's take a look at some more. Another round of graphing and finding the inverse. So here's our original. So we're going back to our parent functions again. So here's your basic square root function. Again, I would list off those coordinates. So I lit them up there for you guys to see those 4 points. As I go down the list, again, 0, 0, not really super helpful because they all have 0, 0. So I don't know which one it is yet, but it's going to show up real quick because I do my 1, 1, and it starts to show my 4, 2 is 2, 4, and my 9, 3 is 3, 9. And there you go. There's your inverse. So again, really easy to identify an inverse, really easy to graph one. If I give you the original, just switch the coordinates. And then again, talking about those reflection ideas, so the A and the C graphs compared to the original, clearly the A, again, if you think about it, is a reflection over the x-axis, and the C graph is a reflection over the y-axis, and then how you'd write it. Okay, so we're doing a little bit of tying that transformation back in just so you guys can, practice that a little bit more. Let's continue on with inverse. So here is the idea of me asking you to draw the original and then its inverse. And if you notice, the function we're dealing with is exponential. So we've already talked about that earlier in the chapter. And what I'm going to do is evaluate the function. So we're going to go f of x equals 2 to the x. I'm going to plug in my x values as exponents because that's how we do exponential. Generate a set of coordinates, then do the coordinate switch. So here we go. Plug in exponent negative 1. Now, reminder, when you plug in a negative exponent, and you want to get rid of that, that's a 1 over idea. So this is really 1 over 2 to the first, or 1/2, and you see our first point pop up. Plug in a power is 0. We all know anything to the 0 power is 1, which also produces the y-intercept. Anything to the first power, is itself. So 2 to the first is 2, and 2 squared is 4. And there's my original graph. And we all know the exponential function look. Doing the inverse idea, again, is just straight coordinate switch. So all I'm going to do is just go down the line and switch, 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 switch. And pops out my inverse. Something else to think about, too, is when we're looking at graphs, besides the idea of just the coordinate switch, I don't know if you noticed it in the previous graph, but there's also a reflection that's going on. That's kind of what we did a little bit of that, talking about reflection in the last 2 slides, over the x-axis, over the y-axis. There's a third kind of reflection, which is unique to inverses, which is the reflection over the line y equals x. So idea here would be if I could pick up this grid and I could fold it, I could put my one fingertip here and one fingertip here and fold it corner to corner, the blue and red dots then would line up perfectly. So another way to kind of know that, like, did I do it right or not, is to check that reflection line and just see, does it look like those points are reflected over that line? And they are. Okay, let's keep going with a few more things here. So the other idea would be that we would, again, sort of work with inverses as a function idea, but not a graph. So when we go to do this, we're going to think about it as coordinate switch. Again, so f of 2, I'm just going to evaluate. Here's my original function. I'm going to plug that 2 in. Just do the calculation, and 2 gives me 7. So what I'm doing right now is saying as I plug 2 in and I get 7, that's a coordinate 2, 7. Over here, if I want its inverse, and the function notation, that little -1 is not an exponent. It actually is a symbol that means inverse. So this is the inverse, f inverse of 7. Well, if this is 2, 7, I know this is 7, 2 as an inverse coordinate. So the f inverse of 7 must be 2. Same thing here, plug in a 5. So I go to plug that 5 in and I get a 5, 13 coordinate. So I plugged in an x, it produced a y. If I do the coordinate switch, 13, 5, so I guess the inverse, f inverse of 13 must be 5. What I don't need to have here is I don't need to see the graph. I don't need to see the inverse function, and we'll do that in a minute, but I can answer the question strictly based on the xy switch. Now, it gets to be maybe a little less clear when you don't get the original, so we don't start with f. But what I'm going to show you here is another way to do this, besides, calculate, then coordinate switch. Is let's say this is all I gave you. What are you trying to figure out? What you want to know is 2 times what number plus 3 is equal to 13. And that you can set up as a little mini equation and solve. So what I could do is take the function set equal to the value I'm trying to evaluate, even though I don't have the inverse, and solve. So again, when I see this number here, my question is 2 times what plus 3 would produce the 5, and I can solve that. Now, the reason I'm saying that this is a good way to go is what if I don't know, I don't have the original, so I can't do the coordinate switch. Then what I do is I do that little mini equation. I say, well, what times 2 plus 3 would equal 23? And then I do a little bit of algebra and solve. So you can answer the question without having done the original plugin, is what we're trying to do here, by setting the number that's in here equal to the original function and then solve. Okay. So there's a little bit more of, working with the idea. Again, the theme for sure throughout is the switch of x and y. No question about that. It happens in every problem, everything inverse. Let's look at a few more. So the last topic we're going to do is talk about how you find an inverse. And there's a set of steps here, and you just got to basically run through these. They're pretty easy to do. The first thing is you're going to be given a function. We're going to want to replace the f of x with y. That's number 1. Then number 2 is to switch their x and y. So physically switch them on the page. Here is your exchange. The big thing about inverses, right? And then the last step is just solve it till it reads y equals, and a little bit of algebra will take care of that. So we'll algebra our way through it. And then when you get done with this, typically we'd write the inverse notation. So we'd say, hey, there you go. There's your inverse function. What I'm going to do is show you guys the graph quick. So I'm going to pop over the graphs for a second. And here's that line, y equals 2x plus 3. Here's the inverse we just found. And here's the reflection line. It's good to sort of, if you ask the graph, to just check that out, right? Is this graph red or reflection of the blue? And it is. And we'll come back to that in a sec. So finding inverse, again, pretty easy to do. Let's do a couple more before we wrap it up. So given x squared, again, replace the y, the f of x with y, switch them, and start solving. Now, between red and blue here, what I did is, remember when you try to get rid of a square, we take a square root. So I square root both sides. In the process of solving, when you take the square root, you create a plus minus situation. And then I replace that y with my inverse notation. And again, I'm going to go to Desmos for a sec so we can check it out and have a look. So here's that one. In order for me to get the plus and minus, Desmos doesn't have a plus minus feature, so I got to put them in separately. So that's actually one function there. But, again, then check out the reflection line, and I got it. All right, let's check out our last pair here. So our last pair is start with a root function. We're going to do the same steps. There's my y for f of x. I'm going to do the switch. And now I'm going to start solving. Now to get rid of a square root, we know we have to square it. So we're going to throw that squared around there. That'll take care of my square root symbol. And then finish up with a little bit of algebra. And we got it. This I'll talk about in a second. I'll show you what's going on there. But there's the inverse function for the root. Let's go over to Desmos and have a look. So here's the original. Now here's the thing about this one is here's what we found, right? And why did I have this statement about when x is greater than 0? And I'll tell you why. Because if I go ahead and graph this, what I'm seeing is more than I should, because this reflected is only this part of the graph. So what I have to do basically is just kind of cut it off and say, hey, well, you know what? You don't get to look at all that. You only get to go here. And when I restrict it a little bit, in other words, when